Hello, dear students. Welcome to the channel and welcome to this playlist in which we are discussing the mathematical operations which will be performed on various types of signals and systems. Up until now, we have seen two videos, and in those two videos, we have seen basic operations, basic addition, multiplication, subtraction, division. We have seen integration and differentiation of different signals. We have also seen in previous video, uh, we have seen series and parallel interconnection of different systems. We have seen the concept of system stability, and we have seen how series and parallel connection affects my systems. Now today we are going to discuss very important topic, but before that, if you haven't seen previous videos and if you aren't aware of the basic signals and basic systems, so I would like to encourage you all to go through the previous videos. And if you are totally blank about signals and system, if you are totally new to this, then I would like to tell you, we have already made a whole playlist on systems, signals and systems. So please check out or check this check the whole playlist out. The link will be available in the description below. And about the previous videos, the link for the previous videos will be flashing on the top right hand side corner of your screens in the I button. So if you haven't checked it out, please go and check it out. Now let's move forward to today's topic. Today we are going to discuss about LTI systems. This is one of the most important and most useful topic or useful type of systems in signal processing. So firstly, let's try to know what is LTI system. Let's try to understand what is an LTI system and where I can find it. So the system which is linear and time invariant are the system which are called linear time invariant systems, and the abbreviation for that is LTI systems. So it is the system which is linear and time invariant at the same time, so we call it linear time invariant systems or LTI systems. And most of the system which we observe in the nature, which we find in the nature, which we work in our daily routine, are LTI systems, which means they are linear and time invariant systems. By the way, if you do you remember the linearity and time invariance property of a signal? We have discussed it in the first playlist when we discussed about signals and systems in details. Even though if you don't remember, let me give you a quick glimpse. The what is the linearity of a system? So a system is called to be a linear when the system satisfies the superposition theorem. So if my system is giving satisfaction for a superposition theorem, then my system will be considered a linear system. And for time invariancy, there is an operation which says if the values of x of t and x of t minus k are equal, then my system is considered time invariant. In other words, you can say if my continuous time signal or discrete time signal, whatever the signal you pick, will be time invariant signal if the time shift in the input will result in the corresponding time shift in the output as well. Okay, so that is a time invariant property. So if you shift your input signal uh, with some unit, then your output signal will also be shifting with some unit. That is your time invariant property. So if your system is linear and time variant, which means your system is LTI system. So that is what we are going to discuss about today. And most of the system which we will observe in nature will be LTI systems. Now let's move to the next slide. Why is it not changing? Okay, so that was your LTI system. Now let me uh, quickly give you a glimpse about in impulse response. Even though you must remember the impulse response from back from previous lectures, we have discussed about impulse responses as well. So when the input of the system is impulse function, then the output will be also impulse response, right? And uh, if you are having this impulse signals as an input or output, then this input and output of LTI system will be related by these four things. First is your impulse response. Second will be the block diagram of your system. Third will be differential equations which you will use for calculations. Fourth will be state space representation. Okay, the state space representation of your system. If uh, you will learn about it in uh, upcoming lectures in future. Okay, state space representation of systems. So these four ways we can uh, relate the input and output of LTI systems. Then the impulse response of LTI system can also be used to study the properties of a system. Like we saw properties of system, what were they? The stability or the memory, right? We saw the causality, if my system is a causal or non-causal system. We have seen invertibility, right? We can also check if my system is a static or dynamic, which means either your system is a memoryless system or does it contain some memory, right? So you can also find these properties of a system based on impulse response of LTI system. Now moving to the next slide. Okay, so uh, coming to this system modeling. So you must have a question now, what is a system modeling, right? So system modeling is used to relate input and output of the system with the help of mathematical equations or block diagrams or state space representations, right? You can use any medium which is possible in the signal system domains. But what do you do basically? You relate the input and output of your system with some medium. That is your system modeling, right? And there are multiple system modeling methods which are used for relating input with output. So first one is impulse response, which we are going to discuss about in today's lecture. Then there is intro differential equations. Then we have block diagram representation, block diagram. Using it you can differentiate it. Then we have state space representation. So these are the representation methods which we have, by which we can do the system modeling. Now let's come to the impulse response characterization and convolution integral. So firstly, the question is, what is convolution, right? What does it do? So the again, what does convolution do? Again, it deals with input and output, but this time of unit signal response. So what does it do? The convolution integral relates the input output and unit impulse response of the continuous time system. Okay, it doesn't matter either continuous or discrete, you can take either, but right now we are talking about continuous time systems, so let's talk about continuous time systems. So what does convolution does? Convolution integral relates input output and unit impulse responses of the continuous time systems. Okay, and it has certain properties which it always follows, and properties will all we will also go through the properties in detail. There are three properties: commutative property, associative property, and distributive property of convolution. We will discuss them in detail most probably in this lecture or the next lecture. Now why convolution? what are the advantages or what are the application of this convolution in the system signal processing work, right? So firstly, if you want to do the analysis of your system, which I just told you that impulse responses are used to do analysis of your system, like determining causality, stability, step response, time invariance, impulse response, or invertibility. So in order to determine that, what do? We use our impulse response with convolution integrals, and by doing that we can do the system analysis. uh, what what are a few other applications? So another one comes when you want to determine the output of the system, and if input and impulse responses are given to us, then we can determine the output of the system, right? We have impulse rating or impulse response, and we have input. Then you can determine what will be the output, and we are just going to we are just about to do the very same thing in this lecture only. So just be with us and let's see what happens. The third point is what it does, it relates input and output and impulse response. So first we saw unit response, now input, output, and impulse response. Fourth point, what convolution does. So convolution can be used to resolve interconnected systems using convolution properties, the properties which I've just talked about, three properties. So with the help of those properties, what we can do, we can use convolution to resolve interconnected systems. Okay, so it can resolve interconnected systems, so it will be very much helpful. And fifth and the last property, and most probably perhaps the most important property of most important application of convolution. What convolution does, convolution helps to represent system in frequency domain with the help of uh, all these transforms. If you have heard about Fourier transform or Laplace transform or Z transform, so we use uh, all these transforms or either of these transforms to represent my system in the frequency domain. Okay, and the convolution plays major role in it, right? So how do we do that? How What do we use to convert my system in the frequency domain? So we use pole zero plots. We can study pole zero plots. By that we can study stability, we can study the filtering, right? We can study all these things with the help of this convolution application, right? Now let's come to the representation of my continuous time signal in terms of impulse. So how do we represent a continuous time signal in a continuous time signal as an impulse signal, right? So let's take a signal, let's call this signal x of t, and let's try to represent it as a weighted sum of impulses, various impulses. Okay, so uh, as you can see here, this signal here, you can see it is weighted sum of impulse responses which we have took, and this point A of my signal, can't we represent it as an impulse as well, right? Here see, on the x-axis we are having time, on the y-axis I am having x of t, my signal, and this point A I am representing it as an impulse tau. Okay, and when I do it, here I write x of t delta t minus tau, because what is it, it is an impulse, right? So what we are doing, we are taking a point A of my x of t system, and we are representing it by the impulse. What impulse we are taking? See here, del t minus tau. Okay, so we are taking del t minus tau impulse. Now what we will do, this function, the function x of t, as it is a continuous time signal, it will have infinite number of points, right? because you can take a point whenever you want. If you want to take point in the difference distance of 1 unit, you can take. If you want to take if you want to consider a point in the distance of 0.00001 unit, then you can also do that, right? Because it is a continuous time signal, so you can calculate time everywhere. So what will happen? This x of t will have infinite points, right? And uh, if as we are having infinite points, we can represent these points by infinite impulses, can't we? Right. Now let's try to integrate all these impulses. When we try to integrate all these impulses at given x of t, what we will get? We will get this formula. X of t will be equal to minus infinite to infinite x of tau del t minus tau into d tau. Okay. And what is tau? Tau is my continuous function. Okay. So the area which will be under this point will be equal to x of t del t minus tau, right? And it will be equal to a. Now let's try to derive the convolution integral for this very system. So again, let's consider this same continuous time system in which my input signal is x of t and my output signal is y of t. So as my input is x of t and output is y of t, can't we write y of t is equals to t into x of t? Now let's do one thing. Let's put the formula of these impulses which we saw, as we can represent any continuous time signal with infinite number of impulses. So what we will do, we will take infinite number of impulses and we will represent this as infinite number of impulses. So instead of x of t, what did I wrote? See, instead of this x of t, I wrote this one, minus infinite to infinite x of tau del t minus tau into d tau. Okay, and I kept t as it is. Now what we will do, as x of tau is the amplitude of x of t at t is equals to tau. Agree, right? What is x of tau? X of tau is nothing but the amplitude of x of t at t is equals to tau, right? So if t is equals to tau, so you can put tau or t instead of each other, and also it will become constant. So as the system is a linear system, can't we write it this way, right? What did we do? Nothing. We just took this t inside and kept it beside my impulse function. Okay, so we did just that. Then in the next step, what did we do? The input, the unit impulse is applied as an input to my system. Okay, and what is it doing? It is producing unit impulse response. So what am I giving? Impulse, unit impulse, and what output is it giving? It is giving unit impulse response. And this unit impulse response, let's call it h of t. Okay, and as my system is a time invariant system, because in the beginning only we have talked, we are going to discuss about LTI system, which is linear time invariant system. So as my system is a time invariant system, the response of del t minus tau, what will be the response of del t minus tau? Want it be h of t minus tau. Again, remember what did we took as h? It is unit impulse response of my system, right? Unit impulse response of my system. And what was the input? Input was unit impulse again, right? Del t or del t minus tau. So what we will be left with? This t into del t minus tau, what we have found. So let's put value of this into this. So when we put value of t del t minus tau here, what we will get? We will get minus infinite to infinite x of tau h of t minus tau into d tau. So what will be left will be yt equal to xt into HT, right? So this formula, this both of these formula are nothing but your convolution integral. Yeah, we call it convolution integral. Okay, and to represent it in simple form, we use this formula: yt is equals to xt, and this symbol is a convolution symbol. It's not multiplication symbol here, it is a convolution system, so it is called yt is equals to xt convolution ht. So that is your derivation of convolution integral. Now let's try to see some of the properties, the three properties which I have also mentioned in the beginning when we were just discussing the convolution. So convolution has three properties. First one is called cumulative property, of convolution. So what happens in this property, it states that convolution is commutative operation. Okay, so as we know, we can let's again take the same system which we took while deriving the integral. So let's take this same system. So this time again y of t will be this much, minus infinite to infinite, x of tau, h of t minus tau into d tau. Now what we will do, something interesting. What we will do, see here, instead of t minus tau we will take m. Okay, instead of this t minus tau we will take m, and as we are taking t minus tau, so of course we have to take the derivative. Instead of d tau, let's take derivative of it. So t will become 0 minus tau will become d tau, so minus d tau is equals to m will become dm. So d tau will be minus dm, where tau will be equal to infinite, m will become minus infinite based on this, right? Because it is having negative value. So when tau will be infinite, m will be minus infinite. When tau will be minus infinite, m will be infinite. Now y of t is equals to minus infinite to y of t will be equal to infinite to minus infinite. Again substituting value of tau instead of x of t minus m. So instead of tau we will mention t minus m, x of t minus m into hm into dm, right? See, we just substituted values. Instead of t minus tau, what did we wrote? We wrote hm. Instead of d tau, what did we wrote? Dm. And as dm was negative, what did we do? We reversed the limits. See, so we did this. Now can't we write when we inverse the limits? See, here we already inverse the limits. Now if I want to inverse the limit again, because I cannot take infinite to minus infinite, so I want to take minus infinite to infinite. So in order to inverse the limits, what did we do? We took this value here, right? We removed this minus and we inversed the limits, right? See, here we are having minus, here there is no minus. We just simply inverse the limits, and the inside part of the whole integral will remain as it is, x of t minus m hm into dm. Now we will just change the order of them. We will write hm first and then x of t minus m into dm. And as m is just a variable, we can also write tau in the given equation. So instead of m, let's simply replace it with tau. So we'll get y of t is equals to minus infinite to infinite h of tau into x of t minus tau into d tau. Now again see, isn't it similar to this one, right? It is nothing but h of t convolution x of t. So from this we can write y of t is equals to x of t convolution with h of t also equals to as h of t convolution with x of t. So that is your commutative property. Now let's move to second property, which is called associative property of a convolution. Here let's first again consider a system. This time we will need two different systems, so we are taking different system. The input for the first system will be x of t, and output of the first system will be y of t. The output of the first system will become input for the second system, and the second system will be called h2 of t, and the output of the second system will be y of t. Okay, and both system are in cascaded connection, series connection. Okay, so seeing this image or connection, can't we say y of t is equals to y1 of t convolution with h2 of t? See again, what is y of t? Y1 of t convolution with h2 of t, right? And again, writing the formula of convolution, we will get minus infinite to infinite y of y1 of tau h2 of t minus tau into d tau. And come back here again, what is y1 of t, right? It is again convolution of x of t and h1 of t. So what we will write, y1 of tau is equals to x of tau into h1 of tau. And again what we will do, we will write the convolution formula, right? Minus infinite to infinite x of m h1 of tau minus m into dm. So here what did we do, we used two separate variables, tau and m. And in the above equation, this one equation, which equation, this equation, let's put the value of okay, sorry, not that, this equation, let's put the value of y of t, right? So what was y of t is equals to y1 of t dot h2 of t. What is the value of y1 of t? This, right? So we will take x of m h1 tau minus m dm, and after that h2 of tau t minus tau into dt. So we took all this here. Y of t will be, we just put the value of y1 of t here and then h2 of t. So this will look something like that. We will have two integrations, x of m h1 tau minus m h2 tau t minus tau dm dot d tau. Now again let's try to put t tau minus m is equals to n, and when we do that we will get some this picture. So instead of tau minus uh, m, we will put simply n. So here we will put n. So what we will get, we will get x of m h1 of n, because it was tau minus m, h2 of, see here, t minus tau minus instead of t minus tau we got t minus m minus n. Okay, t minus m minus n, because instead of tau, can't we write what is the value of tau? It will be n minus m, right? So here we will write t minus m minus n dm dot dn. And again we will consider this interval only. First we will consider h1 dot n dot h2 of t minus m minus n dot dn, and we will keep the x of n and dm and another integral out. So this integration, which is shown by this square brackets, doesn't it looks a little familiar to you? Have you seen it somewhere before, right? It is a convolution formula, right? So it is nothing but this, minus infinite to infinite h1 of n h2 of t minus m minus n into dn, which will be equal to h of t minus m, right? So what we will do, we will simply put this value of this formula which we have just saw in the above formula, right? We will put this formula in this formula simply. So what we will get, y of t will be equal to minus infinite to infinite, which we already have, x of m h of t minus m, this term for this whole term, dot dm, right? So see again, what is it? It is nothing but my convolution formula, x of m h of t minus m into dm, right? So it is same again my convolution formula. So can't we write it, y of t is equals to x of t minus t into h of t, right? Now as we have written that, we can also say that y1 of t will be equal to x of t convolution with h1 of t. See here, y1 of t will be x of t convolution with h1 of t, and y2 of t will be h1 of t convolution with h2 of t, right? So what will be the y of t? Y of t will be y1 of t convolution with h2 of t, right? See here, what is the y of t? H1 of t and h2 y1 of t into h2 of t. So that will be the formulas of your y1 and y. Now in this formula of y2, let's just put value of y1 here. So what we will have x of tau, x of t convolution with h1 of t, right? We will just putting this values here, and the whole term convolve in convolution with h2 of t. So what we will get, right? It is again the same formula. So we will get y of t will be equal to x of t convolution with h of t. So we can write it both ways, this ways as well and this way as well. So that is your associative property, in which x of t cross h1 of t into whole term in convolution with h2 of t will be equal to x of t in convolution with the whole term h1 of t convolution with h2 of t. So that is your associative property. Now coming to the third property, distributive property. So for distributive property, what do we have to do? We have to take two different systems, both in parallel connection. In both we are feeding input x of t, and we are getting output y1 of t from the system h1 of t, and we are getting i2 of t from system h2 of t, and we are adding both of these output, and we are getting combined output of those two y of t. So for this system, what we will do, we have to again calculate, we have to find the distributive property of convolution for it. Okay, so what we will do, our overall output in the parallel will be the addition of both of these systems. So it will be y1 of t plus y2 of t, and writing it in the with the help of convolution, y1 of t will be equal to, what will be y1 of t? It will be h1 of t convolution with x of t. Again, what will be y2 of t? h2 of t convolution with x of t. So we just wrote it down here. So again, instead of the small formula, let's write the whole formula. So minus infinite to infinite x of tau h1 of t minus tau d tau, plus again minus infinite to infinite x of tau h2 of t minus tau. Again we just put the formula, and after putting the formula, what did we do? We wrote as x of tau as it is, and what did we do? We took x of tau common, and in the we took h1 of tau t minus tau plus h2 of t minus tau and into d tau, right? So both of these combined, can't we write them together, h of t minus tau? So we wrote, instead of whole this term, we just wrote h of t minus tau, and when we wrote it, it is nothing but the convolution formula of x of t convolve with h of t. So that is a distributive property. So what it proves? It proves x of t convolution with h1 of t plus x of t into convolution with h2 of t will be always equal to x of t into the whole convolution with h1 of t plus h2 of t. So that is the distributive property of convolution for you. Now that was all the properties of convolution. I will keep this lecture till here. If you have any doubts related to today's lecture or any other lectures, please feel free to mention them in the comment section below. If you have any other doubts, or if you have any feedbacks related to the lectures or anything else, feel free to mention in the comments below. I will be seeing you in the very next lecture. Till then, goodbye. Thank you very much for listening.